Okay, we're going to continue with module 30. Or I'm sorry, module 50. We're almost at the end, right? Module 50. So this one says to multiply these matrices if you can. So they want us to do D times C. So what are the dimensions of D? The dimensions of D are 3 by 3. 3 rows, 3 columns. Then what are the dimensions of C? That also happens to be 3 rows by 3 columns. So these match, and I'll end up with a 3 by 3. So I know I'm going to end up with a 3 by 3 here. Okay. I'm going to use this calculator because this one's a little bit longer. It's not like I just have to multiply 2 numbers together to remember and then add. Now I'm going to have like 3 things that I'm going to multiply together, and sometimes I find it a little bit harder to remember 3 of them. So I am going to use the calculator a little bit just to help me remember the numbers I'm supposed to be adding. Okay? But we are going to apply the same technique. I do like to write my matrices next to each other before you start, just so that I can do that thing I do with my fingers, right? So D goes in the front. And then C will go to the right. And now I'm going to start playing around with the rotation of my hand. Okay, so I know I'm going to end up with a 3 by 3. I know that for sure. I'm going to use my calculator. So these 3 guys times the first row. So 1 times -5 is -5. And it might help if I actually do it this way. Yeah, if I do it this way, then it'll kind of help because you see the color here and you see the top and the bottom, right? So notice that my colored finger is my first finger, and it's over here in the column with the 7. And so then when I flip it over, it's over here, down here with the 1, right? So 1 times -5 is -5 plus the middle guy, which is 1 times -4 plus, and then the guy that had the shiny finger, which was 7 and 1. Okay, so 7. And I get -2. So first row, first column element, first row, first column element goes right here, -2. Do the same row. You have to do the same row for all 3 columns so that you get all 3 entries in the top row. So again, I'm going to put my fingers like this. My shiny finger is my index finger, and it's on the 7. And when I rotate, it's now over here. So this row, or this column, sorry. So 1 times 5 is 5, plus 1 times 6, which is 6, plus 7 times 2, which is 14. 25. Now first row again, right? But times the last column. 1 times 4 is 4. 1 times 4 is 4. And then 7 times 2 is 14. And I get 22. Now we're going to move on to the second column. So that's going to give me all of these entries. So second row. Second row times this. 1 times -5 is -5. 7 times -4 is -28, and 0 times 1 is 0. And so I get -33. Now here we go. I'm just going to do it this way here, and then times my middle. So there's my index finger. 1 and 5 is 5, plus 7 and 6 is 42, plus 0 and 2 is 0. So we get 47. And then middle row times the last column. 1 and 4 is 4, 7 and 4 is 28, and 0 and 2 is 0. And I get 32. Finally, my last row. So last row, first column. -7 and -5 is positive 35. 4 and -4 is -16. 4 and 1 is 4. And I get 23. This times this, so -7 and 5 is -35. 4 and 6 is 24. 4 and 2 is 8. And I get negative 3. And then finally this row times this column, so negative 7 and 4 is negative 28. 4 and 4 is 16, and then 4 and 2 is 8. And so I get negative 4. And that will be a 3 by 3 answer, so I should select a matrix that has 9 little entries, right? And these are the numbers that I'll type in to that matrix. Now, let's see this one. So it wants me to do CD and DC, okay? So let's do CD first, right? Let's work on one first. What are the dimensions of C? The dimensions of C are 3 by 2. And what are the dimensions of D? It's a 2 by 2. So this one, it does match in the middle, and I'll end up with a 3 by 2. Okay. Now what about DC? What are the dimensions of D? The dimensions of D are 2 rows and 2 columns, and the dimensions of C are 3 rows and 2 columns. Notice that in this case, they do not match, right? These do not match at all, which means I cannot do this product, okay? And because I cannot do this product, I'll just say it is undefined. So DC is undefined. So if they had only asked me to find DC, then I would have just been finished just by comparing the dimensions. And I would just say that the problem was undefined, and that's it. I'm done with the problem. However, if they asked me to find CD, because it is possible, I do have to actually go in there and figure it out. So you know me, I like to have this one on the left and this one on the right so I could do my number thing, right? And I'm going to rewrite them even though I don't necessarily need to, because C is on the left and D is on the right. But I'm just going to kind of put them closer to each other. So the guys in this row times the guys in this column. And what am I going to end up with? I'm going to end up with the 3, so 3 rows, but only 2 columns. So that tells me what kind of matrix I'm going to end up with. So this row times this column. 5 times negative 5 is negative 25, plus a positive 30 is positive 5. 5 and 5 times 5 and 0, that's going to be 25 plus 0, which is 25. Now we move on to the second row. Negative 3 and 1 times negative 5 and 6. That's going to be positive 15, positive 6, so positive 21. Here I'm going to get a negative 15 and 0, which is negative 15. Here I'm going to get a negative 20 and a negative 12, which is negative 32. And then finally here I get a positive 20 and a 0, which is just 20. And that is the answer for that product. Okay. Now we're going to move on to something else. I have 2 more topics, and it's called an inverse. So there is a such thing as an inverse matrix. There's only one particular thing that's special about inverse matrices. 2 things actually. One is that some of them don't exist, and you won't know that it doesn't exist until you've tried to find it, and then you determine that it doesn't exist. Okay. The second thing is that only a square matrix, meaning the number of rows times the number of columns must be the same. So a 2 by 2 matrix has an inverse, a 3 by 3 matrix has an inverse, a 4 by 4 does, so on and so forth. But something like a 2 by 1 or 1 by 2 or 2 by 3, things like those do not have inverses. Okay. Now, what is the method to get an inverse? This is the method. You write the matrix that you were given, and then remember this notation, there's the equal sign, right, from solving systems. Well, now what you're going to do is you're going to put the what's called the identity matrix on the right-hand side. When you were solving systems of equations, your job was to make the left-hand side look like this, and then there was a dot, 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 and then whatever you ended up with over here happened to be your solutions, right? Well, in this particular section, we know that that side is supposed to look like. Now what we do is we turn this side into what that side looks like, the identity. 1, 0, 0, 1. We have to get these to look like that. Once we do, however these change, this side will become the inverse. Okay? So right now, the way it's written is you've got A and you've got the identity. Eventually, after we're finished, you want the identity on this side, and what's on that side will be the inverse. Okay? So I'm going to start. How do I turn this into a 1? I have to do 1/3 times row 1 to get a new row 1. And if I do that, this will become 1, negative 2/3, 1/3, and 0 times 1/3 is just 0. And then the bottom row I'm going to keep the same. Now I want to turn this into a 0, which means I need a not positive 9 to cancel that term. So I'm going to do 9 times row 1 plus row 2 so that the 9 and the negative 9 will cancel. And I'm replacing my row 2 because this is where I want the 0. So let's see, 9 times row 1 is 9, and then negative 6, and 3, and 0. Row 2 I'm going to put underneath, and then I'm going to add those puppies together. I get 0, negative 1, 3, and 1. So my matrix turns into this at the bottom and this at the top. And then now, remember, go into the U shape. So the next one, or the diagonal, is going to turn into a positive 1. That's easy to do by taking negative row 2. Just change the signs of all of row 2, right? So row 1 stays the same. Row 2, opposite sign of 0 is still 0. Positive 1, negative 3, negative 1. Now we need to cancel this term, which means we need a positive 2/3 times row 2 plus row 1 to give us a new row 1, because since this is what we want to cancel, we need that 0 to be here. So row 2 times 2/3. 0 times 2/3 is 0. 1 times 2/3 is 2/3. Negative 3 times 2/3 is negative 2. And negative 1 times 2/3 is negative 2/3. Then I'm going to take row 1 and write it right underneath. And then I'm going to add these together. So here I get 1, here I get 0. Here, if you're not sure how to do it, you're going to get negative 5/3. But if you're not sure, you could always use your calculator, right? You can type in negative 2 plus 1 over 3, and it'll tell you it's negative 5/3. This is going to stay negative 2/3. So that is going to become my new row 1. So 1, 0, negative 5/3, negative 2/3, and then 0, 1, negative 3, negative 1. And so what is my inverse? My inverse is only a 2 by 2 matrix, and it's what's on this side. Negative 5/3, negative 2/3, negative 3, and negative 1. Now, let's try another one just to have another example, right? So we're going to start off with our matrix on this side. Hopefully this is an example of what happens when you don't have an inverse, when an inverse doesn't exist, right? Hopefully. We'll see. So there's the identity, and we want to make that side look like that side. So the first thing we do is turn that into a 1 by taking 1/3 row 1. So 1/3 times 3 is 1, 1/3 times 6 is -2, 1/3 times 1 is 1/3, and 1/3 times 0 is 0. Keep the bottom row the same. Change this to a 0, so we need a +2 times row 1 plus row 2 to give us a new row 2, since that's where we want the 0, right? So let's see. We're going to get 2, -4, 2/3, 0. -2, 4, 0, 1, and if I add them together, I get 0, 0, 2/3, 1. So my new matrix becomes 1, -2, 1/3, 0, and then 0, 0, 2/3, 1. Now, my next attempt would be to make the 0 turn into a 1. But you can only multiply by something to turn it into a 1. And it doesn't matter what I multiply by here, nothing I multiply is going to turn the 0 into a 1. Because 0 times anything is still going to be 0. So the fact that I got 2 zeros in this row, this is what tells me that A inverse does not exist. Okay? You can say it is undefined or it doesn't exist. Whatever the verbiage is inside Alex, that's what you're going to use. Okay? But for me, I know that it's not going to work out. If you get a row of zeros down here, or if you happen to coincidentally get a row of zeros at the top, that's your indicator that the inverse does not exist. Okay? So let's try one more problem. This one says, find the inverse of a matrix, or finding the inverse of a matrix to solve a system. Okay, here's the thing. What they're going to do is they're going to turn this matrix into an augmented matrix. We'll use a capital A, times the variables x, y, and that will equal the constant matrix. Okay? Now what they're telling you is that normally when you have something multiplied by or anything that's being applied to your variables, you always use the inverse operation. Like the inverse of multiply is divide, the inverse of a square root is to square, so on and so forth. So whatever your operator is, normally what we do is we apply the inverse on both sides and then it makes this go away. So if I were to apply, let's go down here to the bottom, okay? So let's say I have a matrix A times the matrix variable matrix xy equal to the matrix C. If I multiply the inverse of A on both sides, and remember the side that you choose to put it on matters, right? Since A is right here on the left, that's where I put the inverse. And if I put the inverse on the left on this side, I have to put the inverse on the left on that side. And so when you multiply an inverse times an A, they basically, you can say they cancel each other out or they equal the identity matrix, whichever you want to say. But when you multiply an identity matrix times another matrix, you just end up getting that matrix. So like I said, you can think of them as if they cancel each other out because you're just going to get the X matrix all by itself. And so notice here that you get the variable matrix equal to this product. And then that would tell you X equals something, Y equals something, Z equals something, depending on how big your X matrix, your variable matrix is. So for us, I would write this as, the system can be written as 2, 3, 4, 5 times XY, because those are my variables, equal to 4 times 2, because those are my constants. Now, I also know that this is equivalent to the inverse of this matrix. Oops, I'm sorry. I know that the variable matrix is equal to this, right? Here's what I have. A times the variable matrix times the constant matrix, but it's also equivalent to the variable matrix equaling the inverse matrix of this matrix times the constant matrix. The problem is I have to figure out what this is first, okay? And we have a process to figure this out. So if I want to figure out this, I have to set it up. 2, 3, 4, 5, 1, 0, 0, 1, and then make this side look like the identity. So the first thing I'm going to do is 1/2 row 1, and I get 1, 2, 1/2, and 0. Then I'm going to eliminate the 3 by doing -3 row 1 plus row 2. So -3, -6, -3/2, 0. I get 0, -1, -3/2, 1. Then to make that turn into a positive 1, we're going to do -1 times row 2. So we end up with 1, 2, 1/2, 0, 0, +1, +3/2, and -1. And then we need to turn that to a 0. So I'm going to do -2 times row 2 plus row 1. So 0, -2, -3, +2, 1, 2, 1/2, 0. -3, so it's -6/2, so -5/2, and 2. So then I end up with 1, 0, -5/2, 2, and then 0, 0, +1, 3/2, and -1. And so this side is the inverse, right? This side here is the inverse. So when I come up here, what are they looking for? They want to know what is the inverse that goes right here. And I know what that is now. It's -5/2, 2, 3/2, and -1. What am I multiplying it by? The constant matrix, 4 and 2. And what do I get when I actually multiply that out? So this row times this column, right? And what am I going to end up with actually? There's actually a step in between here that they didn't write out, okay? So I'm going to write it out. The answer is, what kind of matrix will I have? This is a 2 by 2, and I'm about to multiply it times a 2 by 1. These match, which means I can multiply, but what I end up with is a 2 by 1. So 2 rows, but only 1 column, okay? So when I multiply these two things, I'm only going to get one entry. So -5/2 times 4 plus 2 times 2, I get -6. And then here, I'm going to multiply this row times this column. So 3/2 times 4 plus -1 times 2, and I get 4. So notice what this is saying. xy equals -6, 4. So that means x equals -6 and y equals 4. So it's just another method on solving the systems. We did solve the systems by doing it the old way, where you put this here, you put the 4 and the 2 right there, and then you make this side look like the identity, and then whatever's on this side is your solution, right? This is just another way to do it, okay? Now it may seem like there's more work going on for a 2 by 2 matrix, but if I give you a 3 by 3 matrix or even a 4 by 4 matrix, this method may be simpler than just doing it the Gauss-Jordan way. That is it for this module. We'll continue in another video for module 51, which is going to actually cover a third method on solving systems using matrices.